Hello, everyone. I'm Dr. Prathanu Ghosh, and today I'm going to talk about relationship between loading, shear, and moment in a structural beam. So today's lesson objective will be to understand the importance of shear force and bending moment in structural member and establish relationship between external distributed loading and shear force, as well as establish the relation in between shear force and bending moment. So first, we are going to talk about the importance, basically. So importance of shear force and bending moment in a structural member. So why we need to know shear force and bending moment and how it is going to impact in a structural member. As you see the picture, we have one simply supported beam, pin and roller, and we have uniformly distributed load acting in this beam. So as the load is increasing after a certain amount of time, you can see that the beam will develop some amount of cracking from the corner as well as in the middle. So the corner cracking will be developing due to shear, and most of the cracking in the middle is developing due to flexure or bending moment, as well as some cracking may be combination of shear and bending together. So the most important part is to know like how much shear force and bending moment develop at each location in the structural member, so that we can compare the capacity of the beam with the development of shear force and bending moment. How we know the importance? So let's establish the correlation or basically relationship in between shear force and loading. So to do that, again, we pick up one simply supported beam, pin and roller, and uniformly distributed rectangular load is acting, which is W as a function of X. And we will try to establish first relationship between shear and loading in that beam. So for that, we are going to pick up one infinitesimally small element at a distance X, as you see on the top picture, which has length of delta X or dx, and then we blow it up in below so that we can analyze all forces and moment in that infinitesimally small element. So if we focus clearly in below on that small element, as we can observe, we have length delta x to draw the free body diagram. We have shear force from left side upward as the sign convention follows. From right side, it is V plus del V as the incremental shear is happening due to incremental length. Similarly, moment from left side is clockwise M, the other side M plus del M. What else we are having? We are having equivalent concentrated load due to the rectangular distributed load, which is basically area of the rectangle. W as a function of X multiplied by the length of the element, which is delta X, and it is exactly acting in the middle of the rectangle, which is delta X over 2. Now our aim will be to establish the relationships. To do that, we are going to apply our basic fundamental equilibrium equation. Summation of Fy is going to be 0. So if you see very carefully, we have from left side, V is upward positive, W times delta X, which is upward positive, and on right side, V plus delta V, which is going downward, so negative, is going to be 0. So if you simplify, we are obtaining del V is equal to W times delta X. So if we make ratio, delta V over delta X is equal to W as a function of X. So in calculus, we can write down dV over dx is load intensity W as a function of X. If we provide delta X is going to be limit going to be 0. So being said that, we can imagine that from math, we know dV over dx is the slope of the shear diagram basically, and it will be equal to distributed load intensity at each point. So this gives us clear relationship in between external distributed loading and shear forces. So if you little bit elaborate on that, if we take the dx on the other side and dv on left side, and if we integrate in between the 2 points, which is basically shear V1 initial and then shear V2, which will be the integration of the distributed loading. So what we are finding that after integration, V2 minus V1 is equal to basically delta V. The change in shear is equal to area under the loading curve. So another way we can express our relationship in between loading and shear forces. So change in shear in between the points is equal to area under the loading curve. And the loading curve is due to the distributed loading. So now our aim will be the next part, to establish the relationship in between shear force and bending moment. So to do that, again, we are focusing in our same infinitesimally small element, delta x. Now what we are going to do? We are going to take the moment. Instead of taking equilibrium equation of summation of Fy0, we are going to take the moment at point O, as you see the point O on the right side of the element. So is equal to 0. Summation of moment at that point is going to be 0. So if we see very carefully, who are going to create the moments at that point? The first one, V times delta x, which is going to create a clockwise moment. So negative V times delta x. Then what else we are getting? From left side, M is clockwise, negative. From right side, M plus delta M is counterclockwise, positive, as well as the rectangular distributed load, which is W times delta x, and the distance is delta x over 2. So that is also going to create moment. So once you simplify, you are obtaining delta M is equal to V times delta x plus W times half delta x square. So as delta x is very, very small quantity, it's infinitesimally small element. So we can imagine if delta x is very, very small, square of that quantity is almost going to be 0. It is not exactly 0, but it is almost going to be 0. So if for simplicity here, we can, if we assume that delta x square is going to be 0, so the second quantity, which is W times half delta x square, is going to be 0, the whole part. So only thing is remaining, basically delta M is equal to V times delta x. So if you make the ratio of delta M over delta x, which is going to be equal to V. So in calculus, we can express dm over dx is equal to V. If we put the limit of x is going to be 0. So similarly, we can express dm over dx. We know it is slope of the moment diagram, basically from math, which is equal to shear at each point. And if we integrate, taking the dx on the other side, in between the interval m1 to m2, so we see that change in moment m2 minus m1 after the integration, which is equal to delta m, is equal to area under shear diagram. So another way, again, we are establishing relationship in between shear and moment forces. So we establish both part. Again, as a summary, we are talking about establishing relationship in between the distributed loading and shear forces, and establishing relationship in between shear and moment forces. I hope you enjoyed the video, and it will hopefully help you in your next topic.